Okay, thanks for everybody joining. I've got a couple of minutes past 2:30 here. I know a couple of people are coming and going from things, and this has even shifted a little bit. Thanks to making some time here for Sasha to present today. Very interesting idea about radio interferometry and looking at that in like kind of the radio astronomy world. Before we get going, though, thanks for this is to kick off the kind of fall and sort of this whole school year of the Space of ET seminars. Generally, I would have these more in person and have maybe a couple of treats that people could come by um, and snack on, and we'll certainly look for that in 2 weeks. But unfortunately, as you might be able to, if you know me more, tell from my voice, I'm a little bit under the weather. But kind of finishing up that and be in certainly here in 2 weeks. Um, I thought there was something else I was going to mention too. You've got, of course, students who present these are eligible up to awards of $2,500. I do have some, and I'm like very, very close to announcing the ones from last year. My apologies for getting those out so slowly. I think those will work pretty good here. We'll get those out here certainly by the next seminar. And then I do have somebody for 2 weeks from now, and then somebody further into October. But if you are interested in making a seminar or presenting during one of these sessions, feel free to email me. I'd be glad to hear it and glad to have someone on. Um, but uh, but yeah, I think that's about all I want to say. So Sasha, take it away. And Sasha, I want to just say this work is not a part of You've been invited to a conference or you're accepted to a conference in Caltech here in a couple of weeks. Is this some work that you're going to be presenting then, or is this something just different?
Um, no, I won't be presenting it at the Caltech conference. It's more of like a workshop, but I will be presenting it in January at the American Astronomical Society
Okay.
conference.
Okay. Is that sorry, say that again, the American Astronomical Society? Oh, okay. Interesting. Yeah, because so I interrupt you there because is that the one in New Orleans? Okay. So yeah, you might see a couple of people from Virginia Tech there as well. Um, Another project that I'm working on that's coming up in the fall is an eclipse ballooning project. And we have been possibly invited through some colleagues at St. Francis um, to have like a student panel session during that conference. So yeah, very cool. So well, without further ado, I'll turn it over to you and let you take it away.
Hey, thank you so much. I apologize if there's any background noise. I tried to find the quietest places on campus. I'm in the library, but you might still hear people talking. But let me get the right screen. I hope you can see that. Oh, okay. Oh, okay. How do I do this? I accidentally closed my screen. Sorry. I'm trying to do like presenter view, and I've never done that before, so I don't know. Maybe it won't work. Okay. Let me try this. If not, I'll just do regular. That'll be fine. Okay. Can you see that okay?
Yep, I can see that fine.
Okay, let me do this. And okay. Okay, everyone hear me okay? Everyone good? Okay, awesome. Well, thank you so much for coming to the Space of ET seminar today. I am really excited about the project I did over the summer with the National Radio Astronomy Observatory. I worked alongside Dr. Jim Bratz, who is here on Zoom today. Thank you for coming to hear my talk yet again. But I'm very excited to dive into the wonderful world of water megamasers. So we'll start with some background for anyone who's unfamiliar with radio astronomy and what that kind of involves in actual astronomical science. So we'll start with a bit of history. Carl G. Jansky is known as the father of radio astronomy, but his original intent was not actually to discover a new branch of science. He was petitioned by Bell Laboratories, which is the telephone company, to build a radio telescope to observe at a specific frequency. And he built a directional antenna that rotated on this turntable that you can see here. That was actually built from Model T wheels. And it was made to actually rotate so you can see where the actual radio waves were coming from specifically. And after he observed for a few months, he determined that there were three main categories of detections that he made in the radio. The first was from nearby thunderstorms, the second was from distant thunderstorms, and the third was an unknown static, whose intensity rose and fell throughout the day. This is kind of what the spectrum looked like there. As you can see, there was a certain direction where this intensity peaked. And at the time, it coincided with the sun. And so he said, okay, well, this maybe is coming from the sun. So he decided to observe for about a year more. And he noticed that the location of the intensity peak actually changed. And it was determined to be coming from the center of the Milky Way in his perspective. He ended up publishing his findings, but unfortunately, he did that right before World War II. So his findings were kind of shadowed a bit by the politics going on then. But later, we had Grote Reber, I'm not sure how to pronounce his first name there, but he decided that he wanted to actually reobserve what Jansky had seen in the radio. And so he actually built the telescope you can see in this image here himself in his mom's backyard. And this telescope is actually very interesting because it's extremely similar to the design of radio telescopes that we use to this day at our radio observatories. And he ended up detecting eventually the radio emission that Jansky had found after some tweaks in his design. And the thing about his telescope is this is what we consider now a single dish telescope. And I say that because there are single dish telescopes and interferometric telescopes in the radio. So what exactly do those two things mean? Single dish telescopes, as their name kind of hints to, consist of one dish, one parabolic dish. And some of these include the Green Bank telescope, which is in this image, or the FAST telescope, I believe that's in China, which is huge. And then there are also some interferometric telescopes here, like the Atacama large millimeter, submillimeter array, which is this top image, and the very long baseline array, which is this image. And these are called interferometric telescopes because they actually have multiple dishes in their array. It's not just one dish. And we use these because we can actually simulate a larger radio telescope by combining all of the data from these individual dishes. So a bit more to kind of understand, it's very important to understand how your instrument works before you take the data from it. That was a big part of my project, was an entire week boot camp on how these telescopes work. So for single dish telescopes, like I mentioned, there's one dish and it has this parabolic shape that was made so that all of the radio waves that come in actually bounce into the secondary reflector at the top and collect there, and then go towards where we actually take in the data. And telescopes are split into mainly two groups, one called the front end and one called the back end. And so for single dish telescopes, the front end, for let's say like we're looking at the Green Bank telescope, like I showed earlier, the front end actually consists of something called a prime focus, which is this secondary reflector here, and the Gregorian focus here. And on the Green Bank telescope, this is actually a really big turntable that has different receivers in them for the different types of frequencies that we're trying to look at. And so then the back end for, let's say, the Green Bank telescope here mainly consists of two different instrumentations. One is called the digital continuum receiver, or the DCR, and this actually focuses on pointing the telescope, focusing it, and calibration. It's very basic. And then we also have the Caltech continuum back end. This is actually for a specific band called KA, and it helps with things like gain fluctuations and related things to that. And so now interferometers have multiple dishes, as I mentioned, that all have this parabolic shape. And the amount of dishes actually vary per telescope. I can't remember the exact number, but I think if I'm correct, someone can correct me in the chat, but I think there are like 27 telescopes for VLBA or something around that number. So we use a lot of them. And the benefit to these is, like I said, we can actually simulate a larger telescope, which is useful because that actually increases the resolution that we can see. And interferometers also have the front end and back end that I mentioned. So the front end consists of receivers and integration centers that help us take in the data, and the back end consists of converters that change the analog data that the telescope receives and sends over to digital data that we can actually interpret. And all of this is sent into something called the correlator. And the thing that makes interferometry so complicated is the fact that, like I said, we're using multiple telescopes. So this is a diagram here. Let's say you're looking at a source that during your observations is located to the right of the Earth or something in that direction. So in this setup, the telescope on the right actually would receive the signal before the telescope on the left. And obviously that'll result in some issues when you try to interpret those waves together. You'll have something called a phase shift in them. And when you actually take in this data, there's a lot of math that goes into it, and which this is why we have so many integration centers and fancy terminologies that fix this for us. They correct this phase shift and also get rid of any interfering data and give us the nice, beautiful spectra that we see afterwards, or images, either way. And so both of these examples of interferometric telescopes that I mentioned before are located in places like Chile and New Mexico, due to their dry climate and not many people being around, because like I said, there are a lot of telescopes that are involved. But the most famous interferometer, which many people might know more about, is the Event Horizon Telescope. So this telescope consists of 8 different radio telescopes, some of them being single dish and some of them being interferometric, and these are located all around the globe. When all the telescope data was combined together from the observations, it simulated a radio telescope that was the size of the Earth. And the resolution of this data was so sharp that we could actually see something like a supermassive black hole in another galaxy in Messier 87. And then we actually use this telescope again to actually view our own black hole in the center of the Milky Way, which is extremely interesting to me. And this is an image of it here. I think this is the Messier 87 supermassive black hole. So that was a bit of radio background, and now we could finally get into the background of my project and specifically what I worked with, which are water megamasers. So what exactly are these things? So masers are actually exactly like lasers, except they emit in the microwave. And there are 2 main extragalactic masers that we study, the first of which being star formation masers, which are coined kilomasers, and the second are called active galactic nucleus masers, which are called megamasers. And these masers actually are very difficult to detect, and that's because they have very specific conditions that they need in order to have the excitation come towards us and be able to be picked up by our radio telescopes. And so the first condition that we have is the fact that these masers have to be located in dense and warm regions, which coincide to the regions around supermassive black holes. And they also have to be located in something called a Seyfert-2 galaxy. And I have this diagram here on the right that kind of helps us explain what Seyfert-1 and Seyfert-2 galaxies are. So around supermassive black holes, we have something called a torus, which is the shape of a donut. So I have these beautiful donuts here. And when you actually go within this torus, you see the thin accretion disk. Now, in Seyfert-1 galaxies, we are actually looking through the hole of the donut or the torus, and we're actually looking through it to the black hole. But in Seyfert-2 galaxies, we're looking through the side of the torus, and we look in towards the thin accretion disk itself. And this is beneficial because that's how these masers can actually send their excited radio waves towards us into the telescope. So we need this sort of orientation to be able to observe them. And the angle of the orientation actually directly affects our observations, and this can be seen in the Megamaser spectrum. So I have an example spectrum here of ESO 269, and as you can see, there are 3 predominant sections of emission. So because of the orientation of the thin accretion disk, we get these three different peaks here. So the first one is from the front centralmost point of the disk. So this laser here corresponds to this green emission here. And the other 2 are from the sides of the disk, so here and here with the red and blue. And the central maser marked in green, both in the video and in the spectrum, is called the systemic maser. This is because this maser is actually retreating away from us at the velocity of the galaxy, also called the systemic velocity. And the masers that are marked in blue and red are called the high velocity masers. Because of the rotation of the accretion disk, which you can see in this video here, it's rotating from left to right. The masers in the blue are actually blue shifted in their velocity towards us, and the red masers are red shifted away from us. So Another counterintuitive thing that we have to cover for a second here is the innermost masers that I'm pointing to here are actually rotating faster than the outer masers. So the inner maser here is actually represented by the outer emission in the spectrum. And then the same goes for the outer masers to the inner emission of the spectrum here. For the same reasoning, when you go further outside of the disk, you start rotating a bit slower. And we'll get into later how this exactly relates to something that I studied with these masers. So a big question to be answered about this topic is, why do we study these things if they're obviously so difficult to find from all these different conditions that they need and all this crazy particle physics that goes on? Why do we try to study these? What's the point? So they may be difficult to find, but their dynamics are extremely simple. Because of their location, their orbit is typically completely Keplerian, which means that their orbit is dominated just by the black hole and nothing else interfering with it. But they're located far enough away from this black hole so that we can ignore relativistic effects. Megamasers also provide us with a method of getting extremely important values and information. Firstly, masers can tell us the orientation of the accretion disk. As you can see to the right, this disk is relatively flat, but there are also examples of tilted accretion disks as well, as you can see here. These megamasers have also been used to get extremely accurate supermassive black hole mass, and this is a very important area of research going on still to this day on how to get even more accurate masses. And one of the most intriguing things that we can actually get from these megamasers is a direct geometrical measurement of the Hubble constant. If anyone's unfamiliar, the Hubble constant is the measure of how fast the universe is accelerating per distance away from us. And this is actually so intriguing, the research that we're doing with these masers and the Hubble constant, that there is an international collaboration called the Megamaser Cosmology project that dedicates their time to measuring the Hubble constant using these masers. And the masers that have been used to get a measured value of the Hubble constant the masers have been used to get a measured value of the Hubble constant to approximately 73.9 kilometers per second per megaparsec. And this is actually kind of going against the predicted value of 67.4 kilometers per second per megaparsec. And this is extremely interesting because that signifies that there's something either wrong with our predictions or our observations. And obviously, to go further in physics, we have to figure out which one is wrong. And the Megamaser Cosmology project has mainly used something called 22 gigahertz megamasers for these evaluations. Now, what are 22 gigahertz megamasers? What does that mean? So 22 gigahertz megamasers come from the ortho water molecule, which is a water molecule in which both of the hydrogen atoms spins are pointed in opposite directions. And you can see the transition on this diagram here. This is an energy diagram of the water molecule. And so you can see there's this 22 gigahertz transition here to the right on the ortho side. And these 22 gigahertz megamasers are observable using single dish telescopes, like the Green Meg telescope. And we have been able to map the inner regions of these maser disks using something called VLBI mapping, using the GBT, VLBA, VLA, and EFB, a conglomeration of all of them, to get an extremely accurate mapping of the actual disk. And over time, we have actually observed a total of approximately 30 22 gigahertz maser disk galaxies. But on the other hand, we also have something called 183 gigahertz megamasers. And so by similar reasoning, we have the transition on the left-hand side here that's marked with 183 gigahertz, and this is for the para water molecule. And this is when the spins of the hydrogen are parallel to each other. And we were actually unable to detect these megamasers until ALMA gained something called band 5, which observes in this frequency range. And what we can do with these 183 gigahertz megamasers is extremely interesting, and it's mainly because we've never been able to observe them before. So we can study the outer disk and environment around the supermassive black hole using these megamasers. And that's because, as you can see in this diagram, they are excited at a lower energy than the 22 gigahertz. Therefore, they'd be excited at a lower temperature. And so that corresponds to a further distance away from the black hole. So they'd be located further away and also rotating slower than the 22 gigahertz megamasers. And because they're also excited at this lower temperature, we actually think they'd be more easily detectable. They have more of a lenient requirement to be excited in this region. And here's ALMA as well. Like I said, this is the telescope that actually lets us observe these directly, as opposed to before. We did have telescopes that observed in this frequency range, but they just did not have enough resolution for us to be able to detect these maser emissions. So this actually leads to the motivation of this project, which is, can we detect these megamasers in the 7mm, and do 183 gigahertz megamasers coincide with 22 gigahertz megamasers? And that basically means that when we know we have a galaxy with 22 gigahertz megamasers, will we always see 183 gigahertz megamasers, or do they not really appear with each other? Is there no correlation between the two? And both these questions were actually the basis of a study done by Don Pesci, a former graduate student of my advisor, in a 2023 paper, which leads me actually directly into our data section here. So the data that was used for this project was a total of 20 galaxies that were investigated by this paper I just mentioned. All of these galaxies has previously identified 22 gigahertz masers, and then were then observed again with ALMA in search of the 183 gigahertz masers. So for better comparison, this is a lot of data. We're looking at a lot of very noisy lines here. I'm going to look at a subsection of some of these galaxies in the paper. So we have 6 galaxies here on the right. The red line that you see is the 22 gigahertz spectrum, and the black is the 183 gigahertz spectrum. So the paper by Pesci concluded that 13 out of the 20 galaxies that were studied had some sort of 183 gigahertz emission, with 5 having some systemic emission and 8 having systemic and high velocity emission, and 8 having only systemic emission. So as you can see here, this spectrum in the top has systemic and high velocity emission, and the rest really only have systemic going on in the black spectrum on the bottom. So let's see here. Oh, click the wrong button. There we go. So now we'll get into a bit of the method that I got into, and this is the main part of my project. The typical method that astronomers use to look for peaks in data is comparing the general noise of the spectrum to they individually look through every single line in the spectrum and compare it to the average noise. And if they get a peak, say above 3 or 5 sigma, whatever they're looking for, they say that that's an emission detection. And so what I did is I actually took advantage of the fact that we have this triple peaked shape that we're looking for in the data. And I used something called linear cross correlation. And cross correlation is basically a measure of how similar two signals are to each other. So as you can see in the video on the top left, we have 2 different signals going on. The signal in red that is moving across the blue signal is the template, and the blue signal, the blue line, I guess, is the actual signal itself. So as the template comes across this blue signal, you get a cross correlation pattern in the bottom box. The central peak at the center there where it peaks at the top represents where the spectrum is actually perfectly matched to the template, and those signals are completely similar to each other, 100% similar. And so I created a program that actually uses this cross correlation method to analyze the 20 galaxies I was studying. To the right, you can see an example of one of these cross correlations that I did. At the top, we have the triple peaked square template that I was using. That was a variable template. And in the middle, we have the spectrum that I was analyzing. And at the very bottom, we have the cross correlation pattern. So what my program did is at the very beginning of the program, these 2 leftward and rightward peaks started right next to the central emission. And every iteration that it ran, those left and rightward peaks stepped out by 10 channels each. So by the end, they were all the way on the edge, and the central emission was still in the same spot. And every time it moved out 10 channels, it ran a cross correlation of that template over the spectrum, and it analyzed how similar that template was to the spectrum that I was looking at. And so what we have here is actually a best matched template. So this is telling you that this template here and this spectrum here are the most similar out of all of the templates that I ran. And this cross correlation pattern is actually a detection. This is what we would consider a detection, and I'll explain why we're looking for this weird, basically quintuple peaked cross correlation pattern. So I hope you can see me here. Let me see if you can see me. Okay, yeah. So if you have a spectrum with 3 peaks hidden within it, and you're using a 3 peaked template, like in the video, you have them going over top of each other. So when the first peak in the template matches the first peak in the spectrum, you'll get a small cross-correlation bump. And then the template will move over again in the cross-correlation, and you have two of them overlapping, and you get a little bit taller of a bump. And then when all three of them are on top of each other, you'll get the tallest bump right in the middle, and then you'll get two more bumps afterwards for the rest of the template. So you have 5 bumps that you're looking for in your cross-correlation that will tell you that we actually have 3 peaks in the spectrum itself. And obviously, this kind of looks like noise to anyone that doesn't really know what we're looking for exactly. And so we did come up with some verification methods as well to try to determine, is this a noisy cross-correlation pattern, or is this actually what we're looking for? And we'll get into these verification methods here. So one thing that we thought of was, let's say we have our spectrum. So here is the spectrum with the usual cross-correlation run over top of it. And this tells us that we have a nice triple peaked emission happening in our spectrum, this cross-correlation pattern here. So we thought, okay, what would the cross-correlation pattern look like if it didn't have the systemic emission at all? Let's say we were looking for the systemic emission, what would the cross-correlation pattern look like? And so that's this on the left here. As you can see, we have the spectrum in the second box, and we have edited noise in the third box, which is where we got rid of the central emission there. And then we ran a cross-correlation pattern with a double peaked template instead. And of course, it matched perfectly on top of these peaks on the left and right, and it gave us a singular bump in the cross-correlation, which means all you have are 2 bumps there in the spectrum for the high velocity lines. And so then we thought, okay, what happens if we get rid of the high velocity lines and we have just systemic emission, which is kind of the whole thing that I'm looking for with this project. So this is the really useful verification method. So we have our regular spectrum again, and then we have a spectrum where we took out and put in regular, just complete average noise on the left and rightward of the emission. And we ran the cross correlation of this template with this new spectrum that I edited here. And we got this cross correlation bump. So as you can see, there are 3 cross-correlation peaks happening. The central one is like a nice Gaussian looking peak, but the ones on the left and the right have a flat top, and they don't have this kind of upwards trend that peaks that we're kind of looking for. And that's because what this cross-correlation does is it actually takes the peak of this template and multiplies it to the value that it's over top of in the spectrum, and it gives you your cross-correlation value. So all this is doing is just multiplying in my template. So we basically just have a square peak in our cross-correlation, meaning we found nothing. So now that we talked about some verification methods and a lot about our cross-correlation, we can get into some actual results that we got with this program. So here, again, we have a lot of information going on, but these are all of the galaxies that had previously systemic only detections from the Pesce paper. So I'll break down what we're looking at here. We have the template at the top. These are all, also I should add, these are all the best match templates. These are not just a random pull of templates from my program. So this is the best matched template at the top here in this first box. And then we have the spectrum in this second box here, and again the spectrum in the third box. As you saw, I was using that for verification methods later, this third box. So it's the same spectrum in the second and third. And then the fourth box is our cross correlation pattern. And so we have 2 definite detections, which are marked by the red stars, and we have 4 tentative detections that we marked with yellow stars. And so we'll actually look directly at one of our other verification methods we used in our 2 definite detections. So this is J0847. And this is a smooth version of the spectrum with the template actually overlaid on top of it directly. So you can get more of a visual representation rather than the very weird looking cross correlation pattern going on. And so as you can see, we have a systemic emission going on here, which is what the paper originally identified. But on the left and the right, we have these really nice positive peaks going on. And I personally believe with my program strongly that these are high velocity emission lines. And another way, besides this smooth overlay and the 2 verification methods that we were using, is actually the rotational velocity of the accretion disk. So we knew the rotational velocity of the 22 gigahertz disk was 750 approximately kilometers per second. And as I mentioned before, these 183 gigahertz masers should be found further out than the 22 gigahertz. So they should have a slower rotational velocity. And we measured that it does have a slower rotational velocity with this template here of 629 kilometers per second. So using all of this information that we have, we are saying that this is a new disk detection with this galaxy here, which is J047. And the reason why new disk detections are actually extremely exciting in the world of megamasers, as you saw, there are only 30 or so 22 gigahertz galaxies that we've found and used for data analysis with the Hubble constant. We need disk detections to actually be able to measure things like the Hubble constant and the supermassive black hole mass. So when we find systemic only emission, it's not unhelpful, very cool, but it's not the most helpful it could be. It's that we can't pull the most data from it. So as soon as we get a disk detection like this actually adds to our cohort of galaxies we can use to get a more accurate measurement of this Hubble constant that we're getting. And so the other galaxy that we're pretty positive about for having a maser disk at 183 gigahertz is UGC 6093. Again, this is the smooth overlay with the template on top. And as you can see, we have these two regions of positive emission going on. And yet again, a slower rotational velocity as well. So this is another disk detection that we're pretty confident on. Yeah. And so now we'll get into the previous quote unquote non-detections that we had from the Pesci paper. And so again, same breakdown. This is the best match template, the spectrum, and the cross correlation pattern that we got after running the code. And we have 3 detections that we got in this category. The red star for J0126 is actually a disk detection that we have tentatively concluded. And the yellow star for NGC 1068 is a tentative systemic emission detection. And the green star for CGCG165 is a tentative red-shifted high velocity detection. And we'll actually look at all 3 of these because that was a lot of words and it's very hard to visualize. So we'll break down each one of these. So we'll start with J0126. This is our tentative disk detection. So as you can see, this is a very, to the human eye, noisy spectrum going on to the right. But the benefit of my code is that human eye has a lot of error. So that's why we're using computers for a lot of other things. This program is helping us become able to detect things we can't usually find with our own previous methods. And so this triple peaked shape here is really beneficial to kind of overlay. So you can see there's a definite systemic emission here going on in the center. And then we have these 2 regions on the left and the right that are highly suspicious of high velocity lines. And again, this is from our multiple verification methods, this overlay method, the cross correlation pattern, and also the rotational velocity that we got from the program. It is again a lower rotational velocity here. So that was a very big surprise that we found in our non-detection part of our data. And then the next that we're going to look at is CGCG165. This is the tentative red-shifted high-velocity galaxy here. And the template is a bit shifted to the left on top of this positive emission at the right that we see here. And this is actually kind of what we were expecting. When we ran the template for the 22 gigahertz masers in the same galaxy, the same thing was happening with the high velocity. It's not always going to be perfectly symmetric in the detections that we're looking for. So when I saw that this is also a bit off to the right, I kind of concluded that that's fine with me. That's what we saw before. And actually, if I'm remembering correctly, CGCG165 is a generally peculiar galaxy in its maser emission. So the fact that we do see this positive region over here, not necessarily lining up with this template, is something that we are saying is okay for us because it makes sense with our data. And again, we use our verification methods and our rotational velocity, which made us determine that this is a tentative detection. And finally, we'll look into NGC 1068. I'm sorry, this is the galaxy that has weird maser emission, which you can see very strongly to the right. This is a weird looking spectrum. So this central emission is extremely wide, and it does not have any really high velocity emission going on the left and the right. So my template actually bunched up in the middle and matched best all together in one of the very first runs of the program. So this is a very obvious positive central emission going on. So this is a systemic detection for this galaxy. So in conclusion, what to kind of take away from this talk is we detected a tentative 7 more disk masers, maser disks than previously discovered by Pesci in his paper in 2023. And this overall means that the cross correlation was an extremely successful method, and also that 183 gigahertz maser disks are really likely to coincide with 22 gigahertz disks. And this conclusion is strong evidence towards further observations of 183 gigahertz masers using ALMA, and this gives future researchers more motivation to study them even further and begin using them as we did with the 22 gigahertz masers with the MCP. And we can gather even more information about our lovely, mysterious universe. And we do have some future work going on with this project. So with all of these galaxies, we'd like to be able to further categorize and verify things like rotational velocities for their detections. So if we determine that any of our galaxies are of interest, we're going to write a proposal to ALMA to actually observe these galaxies for a bit longer to get more, some better signal to noise ratio on our spectra. And we can do some investigations of the outer maser disk, like I mentioned, and do some further calculations possibly of these two values that I was talking about with the Hubble constant and the supermassive black hole mass. And this program actually I rewrote into a pipeline, which instead of changing any sort of elements within the program itself, it just runs once you start it over however many galaxies you give it. And so we are looking at a data set of around 6,000 spectra from the Green Bank telescope. So we'd be looking at the 22 gigahertz masers. And these were all previously observed before and were determined to have no detection going on. So we're just going to run my code through them to see if there's actually any detection that we couldn't see beforehand. And we will hopefully increase the detection rate of these megamaser disks at 22 gigahertz. And again, if we see any that are of very strong interest or peculiar looking after my program runs them, we'd write a proposal to the Green Bank telescope.
Yeah, very, very good. I'll do the virtual clap. That's a very, very good presentation. Very interesting. No, I come much more from a electrical engineering background and things like that, so I don't know as much on the astronomy side, but am familiar with the cross correlation kind of type thing. So my question kind of is maybe a more of an intro one, and how similar would you expect for like a same black hole, the 22 gigahertz and the 183 gigahertz kind of emissions to be for the masers?
Right, that's actually a really good question. That was actually the original intent of this project, was to run the 22 gigahertz spectrum over the 183 to see what we would get. And that was going to actually be used to try to verify our theory of the slower rotational velocity that we were expecting. So they would be a bit off with the 183 gigahertz emission kind of being closer towards the center than the 22. We ended up not being able to do that exactly, mainly because the spectrum length for the two different telescopes were really different, and my cross correlation pattern was not really sure what to do with it when they were that different from each other. But I did, when I ran through all of the spectrum and all the galaxies, I ran the 22 gigahertz first, and I got a best match template for the 22 gigahertz, and then I started with that template for the 183. And most of them we found weren't 100% similar because of that velocity difference, but some of them were pretty close. Like one of the galaxies I showed, the 22 rotational velocity was 715, and the 183 was 711. So very similar to each other. It kind of just depends on which masers feel like sending excitation towards us.
Okay, yeah, that's to say that, yeah, you kind of got the probably next question I was going to say about, yeah, if they're similar, then use that as your template. And but I could see that's difficult, and so the characteristic of just doing the kind of box and varying that was a good approximation. So other questions from the group here on Zoom? Going once. Going twice. You did an excellent job, I would say, for this kind of audience of doing that intro of explaining kind of what masers were and things like that. I'll say that was very, very excellent, and kind of bringing it up for, at least for me, it not being again, a radio astronomist, it was very good and easy to follow into it. So thank you very much for that. But yeah, one last call for any questions. If not, thank you very much for everybody for joining. Again, like I said, I have a presenter, I believe, in 2 weeks coming up. The person escapes me off the top of my head, sorry, and did not have that, but we will have another seminar here in 2 weeks. It will be on campus, or at least there'll be an on-campus in-person component to it. So we hopefully can see you there. At least that's what I'm planning for now. The plans always change. So we'll hopefully see you there in 2 weeks. And otherwise, thank you, Sasha, again for presenting. And if you'd like to present a seminar here in the future for Space of ET, please let me know. But otherwise, we'll see you in 2 weeks.
Awesome. Thanks so much for having me today.